Introduction to P2PKH. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into P2PKH, which stands for Pay to Public Key Hash. This is the most fundamental and historically most common transaction type in Bitcoin. When Satoshi Nakamoto designed Bitcoin, P2PKH was one of the original transaction formats, and it remains widely used today, though newer formats like P2PKH and P2TR are gaining adoption. Understanding P2PKH is essential for understanding how Bitcoin works at a fundamental level because it demonstrates the basic principles of Bitcoin script, the UTXO model, and cryptographic verification. P2PKH transactions represent approximately 40 to 50% of all Bitcoin transactions historically, though this percentage has been declining as SegWit and Taproot adoption increases. In this presentation, we will explore every aspect of P2PKH in exhaustive detail. We will examine what makes P2PKH unique, how Bitcoin addresses are derived from public keys, the exact structure of P2PKH scripts, step-by-step execution of script validation, detailed examples with real cryptographic operations, security properties, advantages and disadvantages, and how P2PKH compares to newer transaction types. By the end, you will have a complete understanding of how the most common Bitcoin transaction type works at the deepest technical level, including the actual opcodes that execute and the cryptographic primitives that secure your Bitcoins. What is P2PKH? P2PKH, or Pay to Public Key Hash, is a transaction type in which Bitcoins are sent to the hash of a public key rather than the public key itself. This might seem like an unnecessary indirection, but it serves multiple important purposes. First, let's understand the basic concept. In Bitcoin, ownership is proven through public key cryptography. You have a private key that only you know. From that private key, you can derive a corresponding public key using elliptic curve mathematics. Anyone who knows your public key can verify signatures you create with your private key. In the simplest transaction type, called Pay to Public Key or P2PK, Bitcoins are sent directly to a public key, and spending them requires a signature from the corresponding private key. However, P2PKH adds an extra layer by hashing the public key. Instead of publishing your public key when receiving funds, you publish only the hash of your public key. This hash becomes your Bitcoin address. When someone sends you Bitcoins, they are actually locking those Bitcoins to the hash of your public key. To spend those Bitcoins later, you must reveal both your public key and a signature. The network verifies that your public key hashes to the required hash and that your signature is valid for that public key. This two-step verification process provides several benefits. It offers quantum resistance. For example, even if quantum computers break elliptic curve cryptography, they would need to reverse the hash function to derive your public key from your address, and cryptographic hash functions are believed to be quantum resistant. It provides address space efficiency because hashes are shorter than full public keys. And it adds a layer of privacy because your public key remains hidden until you spend. Bitcoin address derivation. Understanding P2PKH requires understanding how Bitcoin addresses are derived from private keys through a series of cryptographic transformations. The process begins with a private key, which is simply a 256-bit random number. This provides approximately 2 to the power of 256 possible private keys, which is astronomically large and ensures that randomly generated keys will never collide. From the private key, we derive the public key using elliptic curve multiplication on the sect P256K1 curve. This curve was chosen by Satoshi Nakamoto and is defined by specific parameters. The public key is a point on this elliptic curve with x and y coordinates. In compressed format, we represent this point with 33 bytes. 1 byte indicating whether y is even or odd, followed by the 32-byte x coordinate. In uncompressed format, we use 65 bytes, 1 byte prefix, 32 bytes for X, and 32 bytes for Y. Modern wallets use compressed public keys for efficiency. Once we have the public key, we apply two hash functions sequentially to create the public key hash. First, we apply SHA-256, which produces a 256-bit hash. Then we apply RIPEMD-160 to that result, producing a 160-bit hash. This combination is called hash 160 in Bitcoin terminology. The resulting 20-byte hash is the public key hash that forms the core of a P2PKH transaction. To create a user-friendly address, we add network identification and error detection. We prepend a version byte, 0 for mainnet P2PKH addresses. We calculate a checksum by double SHA-256 hashing the version payload and taking the first 4 bytes. We append this checksum, then encode the entire result in base 58 check encoding, which produces the familiar Bitcoin address format starting with 1 for mainnet P2PKH addresses. Address generation step by step. Let's walk through the complete address generation process, with detailed explanations of each cryptographic operation. We start with a private key. For this example, let's use a simplified representation, though real private keys would be truly random 256-bit numbers generated by cryptographically secure random number generators. The private key must remain absolutely secret because anyone who possesses it can spend all bitcoins associated with the corresponding address. Step 1 is public key derivation. We multiply the private key by the generator point G on the SECP-256K1 elliptic curve. This operation is a one-way function, meaning it's easy to compute the public key from the private key, but computationally infeasible to reverse the process and derive the private key from the public key. The generator point G is a specific point on the curve defined in the SECP-256K1 parameters. The result is a new point on the curve which becomes our public key. In compressed format, this is represented as a 33-byte value. Step 2 is applying SHA-256. We take our compressed public key and hash it using the SHA-256 cryptographic hash function. SHA-256 takes input of arbitrary length and produces a fixed 256-bit output. The function has important properties. It's deterministic, meaning the same input always produces the same output. It's quick to compute in one direction. It's computationally infeasible to reverse. And a small change in input produces a completely different output, known as the avalanche effect. Step 3 is applying RIPEMD-160. We take the SHA-256 output and hash it again using RIPEMD-160, which produces a 160-bit or 20-byte output. This additional hashing step provides extra security and shortens the final address. Step 4 is adding the version byte and checksum, then base 58 encoding to create the final human-readable address. P2PKH transaction structure. A P2PKH transaction contains two critical script components: the script public key in the output being spent, and the script sig in the input spending that output. Let's examine both in detail. The script public key, also called the locking script or output script, is embedded in a transaction output when someone sends you bitcoins. It defines the conditions that must be satisfied to spend those bitcoins in the future. For P2PKH, the script public key follows a standard template consisting of exactly 5 opcodes and 1 data push. The structure is OP_DUP, OP_ #160, the 20-byte public key hash, OP_verify, OP_ check Let's break down what each element does. OP_DUP duplicates the top stack item, which will be important when we get to script execution. OP_160 pops the top item, hashes it with SHA-256 then RIPEMD-160, and pushes the result back onto the stack. The 20-byte public key hash is the actual hash of your public key, the destination address. OP_verify pops two items, compares them for equality, and terminates with failure if they're not equal. OP_check sig verifies an ECDSA signature against a public key. The script sig, also called the unlocking script or input script, is created by the person spending the bitcoins. It provides the data necessary to satisfy the conditions in the script public key. For P2PKH, the script sig is elegantly simple, containing just two data pushes with no opcodes. The structure is the signature, followed by the public key. The signature is a DER encoded ECDSA signature, typically 71 to 73 bytes, plus a 1-byte SIG hash flag indicating what parts of the transaction are signed. The public key is the 33-byte compressed public key corresponding to the address. When validating a transaction, nodes concatenate script sig and script public key, then execute the combined script on a stack machine. P2PKH script execution. Initial setup. Now we will walk through the complete execution of a P2PKH transaction validation step by step. This is where Bitcoin script truly comes alive, and understanding this execution is crucial for understanding Bitcoin security. The execution happens on a stack-based virtual machine. A stack is a last-in first-out data structure, like a stack of plates where you can only add or remove from the top. When we talk about pushing to the stack, we are adding an item to the top. Popping from the stack removes and returns the top item. Bitcoin script execution processes opcodes sequentially, manipulating the stack. If execution completes with a true value on top of the stack and no errors occurred, the transaction is valid. Let us set up our example. Imagine Alice previously received 0.1 BTC in a P2PKH output. The script pub key of that output contains OP_OP hash 160, followed by Alice's public key hash, which we will call PKHA, followed by OP=verify OP check sig. Now Alice wants to spend this output by sending the bitcoins to Bob. She creates a transaction with an input referencing the output she received. In the script sig of this input, Alice provides her signature SIGA and her public key PKA. The validation process begins by concatenating script sig and script pub key. The resulting combined script for execution is SIGA, PKA, OP_, OP hash 160, PKHA, OP=verify, OP check sig. We start with an empty stack and begin processing this script from left to right, executing each operation in sequence. This deterministic execution ensures every node in the Bitcoin network reaches the same conclusion about transaction validity. P2PKH script execution. Step-by-step walkthrough. Let's execute our P2PKH validation script step by step, watching how the stack changes with each operation. We begin with an empty stack and our combined script. Step 1. Process SIGA. This is a data push, not an opcode, so we simply push Alice's signature onto the stack. Stack now contains SIGA at the bottom. Step 2. Process PKA. This is another data push, Alice's public key. We push it onto the stack. Stack now contains from bottom to top SIGA, PKA. Step 3. Execute OP_. This opcode duplicates the top stack item. The top item is PKA, so we make a copy and push it onto the stack. Stack now contains SIGA, PKA, PKA. Notice we now have two copies of the public key. Step 4. Execute OP hash 160. This opcode pops the top stack item, applies SHA-256 followed by RIPEMD-160, and pushes the result back. We pop PKA, hash it, and push the resulting hash. Let's call this computed hash PKH computed. Stack now contains SIGA, PKA, PKH computed. Step 5. Process PKHA. This is the public key hash that was embedded in the original script public key when Alice received the coins. It is a data push, so we push it onto the stack. Stack now contains SIGA, PKA, PKH computed, PKHA step 6, execute OP equal verify. This opcode pops the top two items and compares them. We pop PKHA and PKH computed. If they are not equal, the script terminates immediately with failure. If they are equal, execution continues. This step verifies that the public key Alice provided actually hashes to the public key hash in the script public key. This confirms Alice is providing the correct public key for this address. If the hashes match, we continue with stack containing SIGA, PKA step 7, execute OP check SIG. This is the final and most important opcode. It pops two items, the public key and the signature. It then verifies that the signature is a valid ECDSA signature for the transaction hash using the provided public key. If the signature is valid, it pushes true, represented as 1, onto the stack. If invalid, it pushes false, represented as 0. Assuming Alice's signature is valid, stack now contains true. The script has completed execution. Since the top stack item is true and no errors occurred, the transaction is valid. Detailed example with hexadecimal data. Let's work through a concrete example using actual hexadecimal data to make this completely tangible. We will start with a private key and derive everything from there, then show the actual bytes that would appear in a P2PKH transaction. Our private key in hexadecimal might look like 0x, beginning with 18, ending with 25. This is a 256-bit number represented as 64 hexadecimal characters. From this private key, we derive the compressed public key using elliptic curve multiplication on sect P256K1. The result is a 33-byte compressed public key, 0x, beginning with 02, ending with 52. The first byte 02 indicates this is a compressed public key with an even y coordinate. The remaining 32 bytes are the x coordinate. Now we hash this public key to create the public key hash. First, we apply SHA-256 to the public key. The SHA-256 of our public key produces 0x, beginning with 0b, ending with 98. Then we apply RIPEMD-160 to this SHA-256 hash. The RIPEMD-160 result is our public key hash, 0x, beginning with F5, ending with 31. This is the critical 20-byte value that will appear in the script public key. To create the Bitcoin address, we add a version byte 0x00 for mainnet, calculate a checksum, and base 58 encode. The result would be an address like, beginning with 1p, ending with US when someone sends Bitcoins to this address. The script public key in the transaction output is OP_DUP, OP_hash160, 0x14, 0x beginning with F5, ending with 31, OP_ verify, OP_ check SIG. The 0x14 is a push opcode indicating the next 20 bytes should be pushed to the stack. When we spend this output, we create a script SIG containing our signature and public key. The signature would be approximately 71 to 73 bytes of DER encoded ECDSA signature data plus a SIG hash byte. The script SIG looks like 0x47 followed by 71 bytes of signature data, then 0x21 followed by 33 bytes of compressed public key. Signature generation and SIG hash types. The signature in a P2PKH transaction is not simply a signature of the entire transaction. Bitcoin uses a sophisticated system of signature hash types, abbreviated as SHA types, which allow signers to commit to different portions of the transaction. Understanding this is important for grasping P2PKH security and flexibility. When creating a signature for a P2PKH input, the wallet must first construct the signature hash, or SHA. This is a hash of the transaction data that will be signed. The process is complex with multiple steps. First, you take the transaction and make a copy. In this copy, you replace all input scripts with empty scripts, except for the input you are signing. For that input, you replace the script sig with the script pub key of the output being spent. Then you serialize this modified transaction and append a 4-byte SHA type flag. Then you double SHA-256 hash this serialized data. The resulting 32-byte hash is what gets signed with your private key using ECDSA. The most common SHA type is SHA-all, represented by the value 0x01. This means the signature commits to all inputs and all outputs of the transaction. The transaction is completely locked and cannot be modified without invalidating the signature. SHA-none, value 0x02, commits to all inputs but no outputs, meaning anyone can change where the outputs go. SHA-single, value 0x03, commits to all inputs and one specific output with the same index as the input being signed. There is also a modifier flag SHA-anyone can pay, which can be combined with the others using bitwise OR. When set, the signature commits to only one input instead of all inputs, allowing others to add more inputs. For standard P2PKH transactions, SHA-all is used almost universally. The signature is created using ECDSA with the SEC P256K1 curve parameters. ECDSA produces two values, R and S, which are encoded in DER format, resulting in a byte sequence typically 70 to 72 bytes long, followed by the 1-byte SHA flag. OP-check SIG internal operation. The OP-check SIG opcode is the core of Bitcoin's security model, making an understanding of its internal operation crucial. When OP-check SIG executes, it performs an ECDSA signature verification, a process that involves several steps. First, OP-check SIG pops two items from the stack, the public key and the signature. From the signature, it extracts the SIG hash flag byte, which is the last byte. Using this SIG hash flag, OP-check SIG reconstructs the signature hash, employing the same process the signer used. It takes the current transaction, modifies it according to the SIG hash rules, serializes it with the SIG hash type appended, and then double SHA-256 hashes the result. This produces the message hash that should have been signed. Now, the ECDSA verification begins. The signature contains two values R and S. The public key is a point on the elliptic curve. ECDSA verification utilizes elliptic curve arithmetic to confirm that the signature was created by the private key corresponding to the public key. This mathematical relationship involves computing a point on the curve using the signature values and the message hash, then checking if this computed point matches a transformation of the public key. The specific details involve modular arithmetic and elliptic curve point operations, but the outcome is a simple Boolean value. Either the signature is valid or it is not. If verification succeeds, OP-check SIG pushes a true value, represented as 0x01, onto the stack. If verification fails, it pushes false, represented as an empty byte array. It is important to note that OP-check SIG does not terminate the script on failure, it merely pushes false. However, in P2PKH scripts, OP-check SIG is the last operation, so whatever value it pushes becomes the final stack value. The transaction is valid only if the final stack value is true and is non-zero. One subtle but important detail is that OP-check SIG includes logic to handle signature encoding rules and public key validation. It checks that the public key is a valid point on the SECP-256K1 curve and that the signature follows proper DER encoding standards with low S values as per BIP 62. Security properties of P2PKH. P2PKH provides robust security through multiple layers of cryptographic protection. Let's analyze each security property in detail. First, Collision resistance through cryptographic hashing. The use of SHA-160, which is SHA-256 followed by RIPEMD-160, provides strong collision resistance. A collision would mean two different public keys producing the same hash, which would allow someone with one private key to spend coins sent to an address derived from a different public key. The probability of finding such a collision is astronomically small, approximately 1 in 10 to the power of 160, making it computationally infeasible with current or foreseeable technology. Second, signature security through ECDSA. The security of ECDSA on the SEC P256K1 curve relies on the elliptic curve discrete logarithm problem. Given a public key, which is a point on the curve, it is computationally infeasible to determine the private key, which is the scalar multiplier. The 256-bit private key space provides approximately 2 to the power of 128 bits of security strength, which is considered very strong. No practical attacks on properly implemented SEC P256K1 ECDSA are known. Third, quantum resistance of address format. While quantum computers running Shor's algorithm could potentially break ECDSA and derive private keys from public keys, they cannot reverse cryptographic hash functions efficiently with currently known algorithms. In P2PKH, your public key is not revealed until you spend. Before spending, only the hash of your public key is known publicly. A quantum attacker would need to reverse SHA-160 to get your public key, then break ECDSA to get your private key. The hash reversal step is believed to be quantum resistant, providing some protection. However, once you spend from an address and reveal your public key, quantum vulnerability increases. This is why address reuse is discouraged. Fourth, protection against malleability. While transaction malleability was an issue before SegWit, P2PKH itself has signature malleability where the S value in ECDSA can be negated to create a different valid signature. BIP62 and BIP146 mandate low S values to prevent this. P2PKH transaction fees and size. Understanding the size characteristics of P2PKH transactions is important because transaction fees are proportional to transaction size in bytes, not the amount being transferred. Let's break down the typical size of a P2PKH transaction. A basic P2PKH transaction with one input and two outputs, which is the most common pattern where you are spending one previous output and creating a payment output plus a change output back to yourself, has the following size components. The transaction version field is 4 bytes. The input count is typically 1 byte for a single input. Each input contains the previous transaction hash, which is 32 bytes, the previous output index, which is 4 bytes, the script sig length, which is 1 byte typically, the script sig itself, which for P2PKH is approximately 107 bytes on average, consisting of about 72 bytes for the signature, including the SCI hash flag, plus 33 bytes for the compressed public key, plus a few bytes for length prefixes, and finally, the sequence number, which is 4 bytes. Each input totals approximately 148 bytes. The output count is typically 1 byte. Each output contains the value, which is 8 bytes, the script pub key length, which is 1 byte, and the script pub key itself, which for P2PKH is exactly 25 bytes, consisting of 5 opcodes and one 20-byte public key hash. Each output totals approximately 34 bytes. The lock time field is 4 bytes. For a transaction with one input and two outputs, the total size is approximately 4 plus 1 plus 148 plus 1 plus 34 plus 34 plus 4 equals 226 bytes. This is sometimes cited as approximately 225 or 230 bytes depending on slight variations in signature size. For transactions with multiple inputs or outputs, you can estimate size by adding 148 bytes per additional input and 34 bytes per additional output. Transaction fees are typically specified in satoshis per byte or satoshis per virtual byte. If the current fee rate is 50 satoshis per byte, a 226-byte transaction would cost 11,300 satoshis, or 0.000113 BTC in fees. This is why consolidating many small UTXOs can be expensive, as a transaction with 10 inputs would be approximately 10 times 148 plus overhead, around 1,500 bytes, costing proportionally more in fees. P2PKH versus P2WPKH SegWit comparison. P2PKH was the dominant transaction type until the introduction of segregated witness or SegWit in 2017, which brought P2WPKH as a more efficient alternative. Understanding the differences helps explain why the Bitcoin ecosystem is gradually transitioning. P2WPKH stands for Pay-to-Witness Public Key Hash and provides the same security as P2PKH but with a different structure and multiple advantages. The key innovation of SegWit is moving the signature data, called the witness, out of the main transaction structure into a separate witness structure. For P2WPKH, the script sig is empty or nearly empty, and the signature and public key are placed in the witness. This provides several benefits. First, transaction malleability is completely fixed. The transaction ID is calculated from the transaction data excluding the witness, so signature malleability cannot change the transaction ID. This was essential for enabling Lightning Network. Second, there's an effective block size increase. SegWit introduced a new weight metric where witness data is weighted at 1/4 the weight of non-witness data. This allows blocks to contain more transaction data while maintaining the 1 megabyte base block size limit. Third, P2WPKH transactions are smaller than P2PKH, typically around 140 virtual bytes for a 1 input 2 output transaction compared to 226 bytes for P2PKH. This translates directly to lower fees. Fourth, P2WPKH enables batch validation through Schnorr signatures when combined with Taproot. Fifth, the witness structure allows for versioning and future upgrades. However, P2WPKH requires wallet and software upgrades. Not all wallets and services supported SegWit immediately, which slowed adoption. P2WPKH addresses use Bech32 encoding and start with BC1 for mainnet, which is visually different from P2PKH addresses starting with 1. Some users found the longer addresses less convenient. There's also the wrapped SegWit format P2SH-P2WPKH, which nests a P2WPKH output inside a P2SH address, allowing SegWit use with addresses starting with 3 for backward compatibility with services that don't support native SegWit addresses. Common P2PKH vulnerabilities and mistakes. When used correctly, P2PKH itself is cryptographically secure. However, several common vulnerabilities and mistakes in its implementation and usage can lead to a loss of funds. First, address reuse is highly discouraged in Bitcoin. When you spend from a P2PKH address, you reveal your public key on the blockchain. While this does not immediately compromise security, it reduces quantum resistance and potentially enables analysis that could link multiple transactions. Best practice is to use each address only once. Modern wallets implement hierarchical deterministic key generation with BIP32, BIP44, and BIP84, automatically generating new addresses for each transaction. Second, weak random number generation for private keys can be catastrophic. If a wallet generates private keys using a weak or predictable random number generator, an attacker might be able to predict or brute force the keys. Multiple instances of this have occurred with faulty wallet implementations. Private keys must be generated using cryptographically secure random number generators with sufficient entropy. Third, nonce reuse in ECDSA signatures is a critical vulnerability. ECDSA requires a random nonce for each signature. If the same nonce is used for 2 different messages with the same private key, an attacker can algebraically derive the private key from the two signatures. This happened with the PlayStation 3 signing key and has affected Bitcoin users with broken wallet implementations. Fourth, the malleability of the signature S value, where both S and -S modulo the curve order are valid, can cause transaction tracking issues. BIP62 and BIP146 enforce low S values to prevent this. Fifth, incorrect signature hash construction can lead to vulnerabilities. The SHA must be constructed exactly according to specification. Errors in implementation could allow signature forgery or transaction malleability. Sixth, insufficient fee rates can cause transactions to remain unconfirmed indefinitely. While not a security vulnerability per se, it can lock funds in limbo. Replace by fee-enabled transactions or child pays for parent can help, but prevention through proper fee estimation is best. P2PKH in wallet implementation. Implementing P2PKH support in a Bitcoin wallet requires careful attention to multiple components, each with important technical considerations. Let's walk through what a wallet must do to properly handle P2PKH transactions. First, key generation and management. The wallet must generate cryptographically secure random private keys. Modern wallets use hierarchical deterministic key generation following BIP32, which allows deriving multiple keys from a single seed phrase. This seed is typically represented as 12 or 24 words using BIP39 mnemonic encoding. From the master seed, the wallet derives keys along specific paths following BIP44 for legacy P2PKH addresses. A typical derivation path looks like M/44/0/0/0/0, where M is the master key, 44 indicates BIP44 purpose, 0 is the coin type for Bitcoin, the first 0 is the account number, the second 0 indicates external addresses versus change addresses, and the final 0 is the address ID. The wallet must securely store private keys, preferably encrypted with a password. Second, address generation. From each private key, the wallet derives the public key, hashes it with #160, adds versioning and checksum, and base 58 encodes to create the address. The wallet must track which addresses have been generated and used. Third, UTXO tracking. The wallet must maintain a database of unspent transaction outputs belonging to the wallet's addresses. This requires monitoring the blockchain for incoming transactions to wallet addresses and tracking which outputs have been spent. Full nodes can do this directly from blockchain data. Light clients typically use simplified payment verification, or SPV, with Bloom filters, though this has privacy implications. Modern light clients might use compact block filters following BIP157 and BIP158. Fourth, transaction construction. When the user wants to send bitcoins, the wallet must select appropriate UTXOs to spend, a process called coin selection. Strategies include selecting the smallest UTXOs first to clean up dust, selecting the largest UTXOs to minimize fees, or more sophisticated algorithms. The wallet creates transaction outputs for the payment and usually a change output back to a new wallet address. Fifth, signature creation. For each input being spent, the wallet constructs the signature hash according to the SHA hash type, signs it with the appropriate private key using ECDSA, and constructs the script SIG with the signature and public key. P2PKH transaction anatomy. Let's examine the complete anatomy of a P2PKH transaction at the byte level to understand exactly what data is transmitted and stored on the blockchain. A Bitcoin transaction is a data structure that consists of several fields arranged in a specific order. The first field is the version number, a 4-byte little Indian integer. For most Bitcoin transactions, this is beginning with 0x01 and ending with 00, representing version 1, though version 2 transactions exist to enable BIP68 relative lock times. The second field is the input count, a variable length integer or variant, indicating how many inputs follow. For a single input, this is simply 0x01. For larger numbers, variant encoding allows efficient representation, following the input count or the actual input structures. Each input contains 5 components. First is the previous transaction hash, which is the 32-byte hash of the transaction containing the output being spent, stored in reverse byte order. Second is the previous output index, a 4-byte little Indian integer, indicating which output of that transaction is being spent. Third is the script sig length as a variant, followed by fourth, the actual script sig bytes. For P2PKH, this is approximately 107 bytes, containing the signature and public key. Fifth is the sequence number, a 4-byte value originally intended for transaction replacement, now used for relative time locks with BIP68. Following all inputs comes the output count as a variant, then the actual outputs. Each output has 3 components. First is the value, an 8-byte little Indian integer, representing the amount in satoshis. Second is the script pub key length as a variant. Third is the actual script pub key bytes, which for P2PKH is exactly 25 bytes. Finally, the transaction ends with the lock time field, a 4-byte integer. If 0, the transaction is valid immediately. If less than 500 million, it represents a block height before which the transaction is invalid. If 500 million or greater, it represents a Unix timestamp. The entire transaction structure is serialized into bytes, and this byte sequence is what gets broadcast to the network and included in blocks. P2PKH in Bitcoin history. P2PKH has been part of Bitcoin since the very early days, and understanding its historical context provides insight into Bitcoin's evolution. When Satoshi Nakamoto launched Bitcoin in January 2009, the original implementation supported 2 main transaction types: pay-to-public key, or P2PK, and pay-to-public key hash, or P2PKH. The very first Bitcoin transaction in Block 170, where Satoshi sent 10 BTC to Hal Finney, actually used P2PK, which publishes the full public key in the script public key. However, P2PKH quickly became the standard because it offered better privacy and potential quantum resistance. The Bitcoin addresses we recognize today, those starting with 1 on mainnet, are P2PKH addresses. This format was standardized very early and has remained backward compatible throughout Bitcoin's evolution. In the early years, transaction fees were negligible and block space was plentiful, so the slight inefficiency of P2PKH compared to potential alternatives was not a concern. The focus was on security and simplicity. As Bitcoin grew and blocks began filling up around 2015 to 2017, the Bitcoin community debated scaling solutions. This led to the SegWit soft fork in August 2017, which introduced P2PKH as a more efficient alternative to P2PKH. SegWit adoption was initially slow due to wallet and exchange upgrade requirements, but has gradually increased. As of 2024, SegWit transactions represent the majority of Bitcoin transactions, though P2PKH remains significant. The activation of Taproot in November 2021 introduced P2TR, an even more advanced transaction type with better privacy and flexibility. However, P2PKH continues to be used and supported because of Bitcoin's commitment to backward compatibility. Transactions created with P2PKH today will remain valid forever. Nodes will always be able to validate P2PKH transactions because the opcodes required are part of Bitcoin's immutable consensus rules. This backward compatibility is a cornerstone of Bitcoin's design philosophy, ensuring that the network never fragments and past transactions never become invalid. Advanced P2PKH topics. For those seeking deeper understanding, several advanced topics relate to P2PKH transactions. First, let us discuss signature grinding and fee optimization. Because ECDSA signatures have variable length, typically between 70 and 72 bytes, Some wallets implement signature grinding where they generate multiple signatures using different nonce values and select the shortest one. This can save 1 or 2 bytes per signature, reducing transaction size and fees. While computationally more expensive, this optimization is worthwhile for large transactions with many inputs. Second, there is the concept of script optimization and non-standard scripts. While P2PKH follows a standard template, Bitcoin script technically allows variations. You could create non-standard scripts that achieve similar functionality but with different opcode sequences. However, most nodes only relay and mine standard transaction types by default. Non-standard transactions require direct miner contact or custom node policies. Third, there is the relationship between P2PKH and multi-signature transactions. While P2PKH involves a single public key, multi-signature transactions require multiple keys. Before P2SH was introduced, bare multisig was possible but inefficient. P2SH enabled much better multisig implementations by moving the script complexity from script pub key to the redeem script revealed in script sig. Fourth, there are interesting interactions between P2PKH and time locks. You can create P2PKH outputs with n-lock time or n-sequence restrictions, though this is uncommon. More typically, time locks are combined with P2SH to create more complex scripts. Fifth, there is the concept of address collision resistance. With 2 to the power of 160 possible addresses, the probability of accidentally generating the same address as someone else is negligible, but this has interesting theoretical implications. If 2 people did generate the same private key, they would share the same address and could both spend funds sent there. This is why cryptographically secure randomness is absolutely critical. Sixth, there are advanced fee estimation techniques that consider mempool state, recent block history, and transaction priority to calculate optimal fees for timely confirmation. P2PKH debugging and troubleshooting. When working with P2PKH transactions, developers and advanced users often need to debug issues. Let's explore common problems and how to diagnose them. First, if a transaction is rejected with script validation failure, you need to determine which opcode failed. Bitcoin Core provides detailed error messages in debug mode. Common issues include signature verification failure from OP check sig, which could result from an incorrect signature, wrong public key, or signature hash constructed incorrectly. If OP equal verify fails, it means the provided public key doesn't hash to the required public key hash, indicating you're trying to spend from the wrong address or using the wrong private key. Second, transactions might be rejected for non-script reasons. Insufficient fees can cause transactions to remain in the mempool without confirmation. The solution is either replace by fee if enabled, or child pays for parent where you spend the unconfirmed output with a higher fee. Double spend attempts where you try to spend the same UTXO twice will be rejected. Only one will be accepted into the blockchain. If you sent the first with too low a fee, you might want to replace it, but this requires the transaction to signal replaceability with sequence numbers less than beginning with 0xFF ending with FE third. Transaction malleability can cause confusion. Before SegWit, someone could modify a transaction's signature slightly without invalidating it, changing the transaction ID. This meant you couldn't reliably build chains of unconfirmed transactions. SegWit fixed this for SegWit transactions, but P2PKH transactions remain malleable. Fourth, there are tools for debugging. Bitcoin Core's debug console provides commands like getRaw transaction, decodeRaw transaction, and test mempool accept, which help analyze transactions. Online block explorers show transaction details. Bitcoin script debuggers allow stepping through script execution opcode by opcode. For developers, test networks like testnet and regtest allow experimentation without risking real bitcoins. Fifth, understanding error messages is important. Common errors include bad transactions inputs missing or spent, meaning the UTXO you're trying to spend doesn't exist. mandatory script verify flag failed indicating script validation failure, and minimum relay fee not met indicating insufficient fees. Conclusion and key takeaways. Let's consolidate our comprehensive understanding of P2PKH. Pay to public key hash is the most fundamental and historically important transaction type in Bitcoin. It combines public key cryptography through ECDSA with cryptographic hashing through SHA-256 and RIPEMD-160 to create a secure, efficient system for transferring value. The key insights are as follows. First, P2PKH provides strong security through multiple cryptographic layers. The double hashing with HASH-160 provides collision resistance and potential quantum resistance. ECDSA signatures on the SECP-256K1 curve provide proven security against current attack methods. Second, the script validation process is deterministic and verifiable by any node. The stack-based execution of OP-DUP, OP-HASH-160, OP=verify, and OP-check-sig provides clear, auditable logic for determining transaction validity. Third, P2PKH addresses starting with 1 on mainnet are universally recognized and supported. Backward compatibility ensures P2PKH will remain valid forever. Fourth, while newer transaction types like P2PKH and P2TR offer improvements in efficiency, privacy, and functionality, P2PKH remains relevant and widely used. Fifth, understanding P2PKH deeply provides the foundation for understanding more advanced Bitcoin features. The concepts of UTXOs, scripts, opcodes, signature hashing, and transaction validation all originate from or are demonstrated in P2PKH 6. Proper implementation requires attention to security details including cryptographically secure random number generation, avoiding nonce reuse, proper signature hash construction, and careful key management. For anyone working with Bitcoin, whether as a developer, analyst, or advanced user, P2PKH understanding is essential. It represents the elegant simplicity of Bitcoin's design, where a few well-chosen cryptographic primitives and a simple scripting language combine to create a secure, decentralized monetary system. Thank you for your attendance and detailed exploration of P2PKH. Thank you for your attendance. Please consider subscribing to the channel.